We're going to do a brief little follow-up to the vector addition video segment. And as you might recall from one of our examples, we have two vectors drawn visually, vector u and v, and we did the vector addition. I showed you more than what you see here, but I want to come back now and look at the first vector operation we had, which was magnitude. If we were to compute the magnitude of vector u, the square root of 2 squared plus 6 squared, that'd be square root of 40. That would be the length of this vector here, root 40. And then the magnitude of vector v, square root of 3 squared, which is 9, 1 squared is 1, square root of 10. I could write that in here or at the top. Remember, so long as the direction and the magnitude are the same, this is vector v and this is vector v. They are both vector v. If they are line segments or directed segments where a starting point makes a difference, then we would say they're not different vectors, they're just different lines or parts of different lines. Now, if we were to approximate this square root of 40, we know to be larger than 6, since the square root of 36 is 6. And the square root of 10 is, well, that's right, it's larger than 3. And if we were to add those two magnitudes together, we would have a value that's, well, at the very least it's bigger than 9. I guess it's possible that it's larger than 10 also. I'm going to call it 9 point something, because I really do think it is 9 point something. But without a calculator, I can just do a quick little approximation. So what if we were to find the magnitude of the resultant? The magnitude of vector 5, 7. Or the magnitude of u plus v. Not separately, but we do the addition first and then find the magnitude. That would be square root of 25 plus 49, square root of 74. And I think you will find that is approximately equal to, well, it's less than 9. It's 8 point something. So, does that make sense on the picture? Square root of 74, square root of 40, square root of 10, and I claim that your geometry teacher would say this is exactly what we would expect. It is sometimes called the triangle inequality. The two shorter sides of the triangle will always add up to greater than the third side of the triangle. The only way it is possible for this sum to be equivalent to the sum is if these vectors were linear. They lined up in the same line path, which they do not in this case. So a common little notation for this is to state that the magnitude of the resultant is always less than or equal to the sum of the individual magnitudes. It may not come in as a big deal very often, but if you're proving statements related to distance and magnitudes of forces, this is a pretty handy little inequality to be familiar with. So, come back next time and we might be seeing some new vector operations.